this is this okay?
Yeah, that works. That's very good.
Yeah, whenever you want to start, it's okay.
Thanks. So you can hear me. You can hear me okay?
Yeah, we hear you well.
Okay, great. So thanks a lot for having me in your seminar series. It's a great honor, and it would be great to get to know some of the people here better. So I'm delighted to present this work, which is joint work between Eric Finster and David Reuter. Eric being at the University of Cambridge, myself being in Bonn. This work has been on the archive. We have an implementation as well, computer implementation, which you can get from this link. Okay, so strictly unital infinity categories. So let's talk about these. So suppose we're working in some higher category. You could imagine that we're in a two-group void. And suppose we've got these things to play with. So what do I mean by this? We have objects X and Y. So star means something's an object. This is like a bit of a computer science notation, which I'm going to be using quite a lot, although I'm not really going to be assuming any computer science knowledge. So whenever we have something with a colon, that means like this thing has got this type. And star is going to be the type of objects. So X is an object, Y is an object. F goes from X to X, G goes from X to Y. So these things are one morphisms. H goes from X to Y, J goes from X to Y. These are one morphisms as well. And then mu goes from F to X, nu goes from G to H, zeta goes from H to J. So these are two morphisms. Right? We can tell that because their source and target are one morphisms. So if we know we've got these cells in our two groupoid, then of course we know we can compose them. So let's think about this composite we might want to do. So here we have mu going from F to the identity on X. That's correct. We have nu going from G to H. That's correct. And we want to compose them with zeta, which goes from H to J. But this is wrong, right? Because here, zeta is being pasted in with the source identity composed with H. But that's not allowed, right? This is an invalid composite in a weak 2 category because the source of zeta is not H. It is not the identity composed with H. The source of zeta is H. So when we write this, we can say, okay, I know what you mean, but that's not really valid syntax. Okay, so what is the valid syntax that describes this more accurately? Well, we might write something like this instead. So the difference now is that we're inserting an extra 2 cell, which we could call a unit, a lambda, that's a typo, I should say lambda H. So that's an isomorphism between the identity composed with H and H. And if we put this in, then we can say, okay, this composite is well defined. That makes sense. So it makes sense in a weak 2 category. But it was sort of a pain to have to do that. It was kind of obvious that that's what we meant, right, in some sense when we did this composite number 1. So okay, but obviously, if this is a weak 2 category, we're mathematicians, we have to make composites that are actually valid, right? So we make this composite number 2. So the point about this work is that this distinction is really annoying because it seems like this already contained all of the intuition about what I wanted to do. And to go from 1 to 2 was just bureaucracy, right? So why can't mathematics do this for us automatically? That's what this project's about. This is just about the unit structure. And okay, not every weak 2 category has got strict units, definitely. But probably it's the case that, every weak 2 category is equivalent to one with strict units or something. So shouldn't we be able to use those facts to be able to write this as a shorthand for this more complicated thing? So this is the sort of thing we want to understand, but in the more general context of infinity categories. So ideally, just to say a few concrete things, we'd like to recognize 1 as, okay, it's invalid, but we recognize it is valid up to units, right? You could think of, we recognize 1 as being valid in a strictly unital infinity category. On request, take this composition expression that's valid in the strict setting and inflate it back into 2, right? Back into the corresponding expression. Oh, I'm being told someone is in the waiting room. I have the power. I'm going to let them in. All right. Inflate 1 to 2, inserting the missing coherences. That would be great. And also on request, if we have 2, expression 2, which is complicated, deflate it back into expression one by throwing away, for example, this uniter, saying, yeah, I know that's supposed to be there, but it just makes it more complicated to understand. I want this simple expression. So we're going to do this first one in this talk. We're going to see how to do this for infinity categories. And we're going to see how to do this third thing for infinity categories. And this second thing, we sort of know how to do that, but we haven't worked out all the details, and that's still work in progress. And if we could do that second thing, that would mean that we've proved that every infinity category is equivalent to a strictly unital infinity category. That's something we're working on, but we haven't quite finished that. Okay, so a bit more about a plan for today. So first of all, I'm going to introduce Catt, which is a type theory. So maybe not everyone here will know about type theory, but that's okay because I'm going to introduce it in a really simple, basic way, and it's a really beautiful idea. And actually, as far as I'm concerned, it is the easiest way to understand what a weak infinity category is. We're going to do the whole thing in about 2 pages, the whole definition. So even if you just care about weak infinity categories, then this is a reason for you to be interested in type theory. This was introduced by Eric Finster and Samuel Mimram a few years ago. And then we're going to explain how to take expressions in this type theory. So expressions in this type theory are going to represent composite morphisms. And then we're going to show how to simplify these expressions in the type theory to represent the corresponding, like, strictly unital morphisms where we've removed all the unit structure from our composites. Then we're going to define a new type theory, Catt-SU. So Catt is categorical type theory. So this is the type theory for strictly unital categories. So this gives us a nice type theory for strictly unital categories. Great thing about doing things with type theory, by the way, not only does I think it make it very easy to understand what's going on in a talk like this, but also, of course, we can tell a computer how to do it, right? So we can get computers to help us check our composites and help us form big composites and so on. So then we're going to define what a strictly unital infinity category actually is. We'll explore some of their properties. And then we're going to investigate some non-trivial applications to topology, because higher category theory is, of course, very closely related to topology. So the danger when I'm giving a little meta comment, the danger of giving online talks is you feel like you're a crazy person trapped in a room by yourself, right? Which I probably am. I definitely am. But please, I really want you to feel free to unmute yourself, if that's okay with the host, and just ask questions. And that would really make me feel like I'm understanding what you guys are thinking. Of course, if you type things in the chat, right, I can't see that. So I much prefer you just interrupt me and say, wait, what does that mean? And stuff like that. Okay, so now I'm going to introduce you to this type theory. So again, if you haven't really seen type theory before, you don't really know what it means, or maybe you've heard of it, but you think it's super complicated. Really, it isn't. It's just really a notation. It's a very precise and clean notation, which is really useful for subjects like higher category theory, which are technical and where we could easily make a mistake, right? A notational error or something like that. So it helps us keep organized. So first of all, we have contexts. These are these capital Greek letters, and they're lists of variables with types. And these variables we can think of as generators for a free infinity category. So X is some generating morphism. It's got some type A. Y is some generating morphism. It's got some type B, and so on. If a context is valid, and we'll see later why context could be valid or invalid, we write this silly thing. This is called a turnstile. It just means gamma is valid. It's not malformed. And we interpret this mathematically as follows. Gamma is the generating data for a free infinity category. And we call that gamma tilde. So let's think about monoids, right? If we have a set, then that's the generating data for a monoid, which is the words on that set, right? Of course, there's a difference between the set and the monoid that it generates. So gamma is the generating data, and gamma tilde is the free infinity category generated by taking these variables, these generating morphisms, 2 morphisms, 3 morphisms, and composing them together. Okay. Types, ABC, and so on, capital Roman letters, are trivial. This means the type of objects, or they're pair of parallel terms. We'll see what terms are in a minute. Terms just mean morphisms. And if we've got some type that's valid, then we write gamma in the infinity category gamma. Then we write gamma turnstile A. And again, this has a very simple interpretation. In the free infinity category on gamma, there is a Hom set A. So star is like the Hom set that contains the objects. So that's like a fake extra Hom set that's convenient. So we can pretend that the objects are in a Hom set. And if U and V are a pair of parallel morphisms, then U arrow V is a Hom set in our infinity category, right? That makes sense, I hope. Shout out if it doesn't. Now, terms, a term is just this silly type theory word. It's just going to mean a morphism, potentially an atomic morphism, a generating morphism, or potentially a composite morphism in our infinity category. So if it's a generator, one of these variables, we just write X. You see, it's just like one of these generators up here. Otherwise, it can be something called a coherence or a composite. We'll see what these things mean later. Coherences are like laws, like associativity, for example. Well, they're all weak structure, but they're like the associator, for example, or interchanger or a uniter, so weak higher structure. These composites, these are a way to compose, say, some N cells to get another N cell. So like binary composition, something like that. And these guys we can interpret as morphisms. And if one of these guys is well formed, that is, we've used this type theory correctly to build it, then we say gamma turnstile U colon A. We interpret that as saying in the free infinity category on generated by gamma, there's a cell U, a morphism U in the Hom set A. So that's all we've got. We've got infinity categories, morphisms, and those morphisms are in Hom sets. And we're using this type theory notation. It really fits really beautifully. And then finally, we got this notion of substitution. A substitution is supposed to be like a strict infinity functor. But remember, these are free infinity categories. So if you want to have a monoid homomorphism between free monoids, we only need to say where the generators go. And it's exactly the same for us. So all we need to give is a function from the variables, the generators of gamma, to the terms, which are the morphisms of delta, potentially composite. So it's a function like this, has to satisfy some properties, some axioms. And then we interpret this as saying there is a strict infinity functor, sigma, from the free infinity category on gamma to the free infinity category on delta. And then the point about setting this up as a type theory is the type theory tells you which contexts, which types, which terms are valid, which ones aren't, in a way that's so easy you can tell it to a computer. So it takes away some of the technical difficulty of working with infinity categories. Now, these contexts that we use, these contexts play an important role, these contexts gamma, because we use them to form these coherences, which are like our laws and our composites. You see, they appear here in the syntax. So let's understand what's happening there. Pasting contexts are really, really important ideas in the theory of high categories. I guess many people here have heard of pasting contexts, and they correspond combinatorially to these things called Batanin trees, which I'm sure many people have also heard of. So I'm going to illustrate this by giving an example. I'm going to give it 3 ways. Okay. Think of it as starter, main course, and dessert, if you like. Okay. So here we've got some generating object X in our infinity category. We're also going to represent it as an element of a tree here, and as a list here. This is the type theory expression. So this is X colon star. X is an object. That's all that means. Now suppose I want to add, I want to do a little extension of my context. I want another object Y and a morphism F from X to Y. So we could draw it like this in terms of, ordinary category notation. In terms of our tree, we add a new leaf to our tree. We label the leaf F, and the source and target of F, X and Y respectively, we put on either side of the bottom of the edge. And here we just record what we've done as a list. So X was an object, Y is another object, and F goes from X to Y. Now I'm going to add 2-cell mu going to some G. So what did we have to add? Well, we had to add G also going from X to Y, and now mu going from F to G. And mu has appeared as an extra leaf here, right? Now I'm going to add nu. Nu goes from G to H. And I've added this up here. So all of the combinatorial structure from this perspective, we can also see here. So the source of nu is G. We can see that here by taking nu and going down on the left, we get to G. The target of nu is h, and we can see that by taking nu and going down on the right-hand side, and we get h. So you see what's being drawn here is exactly the same as what's being drawn here, just a different notation. But the interpretation between these pictures is very shallow, right? But yet it looks completely different. So it's nice to have these different representations for these things called pasting contexts, which is so important for high category theory. And here again, of course, as before, we're still just collecting the list of all our generators, all our cells. And now this is going to be the last thing. We're going to add one morphism J from Y to Z. So it goes on here. We can check its source is Y, its target is Z, it's gone on here. Another little useful trick is that if we want to know what dimension something has, so J is a one cell, we look at the height it appears. So look, F, G, H, and J all appear at height 1, and they're the 1 cells. X, Y, Z appear at height 0, and they're the 0 cells. Mu and nu appear at height 2, and they're the 2 cells, right? That matches. So that all makes sense. Now, some of these variables are leaves of the tree. They're the variables here, mu and nu and j, which are not the boundary of some other variable. We call these locally maximal. We can identify them easily because they're the leaves. And somehow, if you know like what's happening with all the locally maximal variables, you know about everything, because between them, they sort of span the whole geometry of the pasting diagram. That makes some sense. Now, we can also talk about the boundaries of these pasting contexts. So, for example, what's its upper boundary? It's x, h, y, j, z. And we call that delta plus, right? If this is gamma, then that's this delta plus of gamma. X, h, y, j, z. It's just this thing across the top. Oh, someone in the waiting room. It's hotting up in that waiting room. Okay, I'm not the only host. You can let people in, can you, Juan? So I don't have to. I see.
Yeah, sure.
I thought maybe I was the only host. I don't know, because I know Zoom sometimes is a bit funny. Okay, it's good that I'm not. Okay, and then there's a lower boundary, delta minus, x, f, y, j, z. Great. It's along there. So how do we build terms? How do we build composites in this type theory? Right? How do we build composite morphisms in this approach to weak infinity categories? So we use this law, which again is written in type theory notation, which looks a bit off-putting, but it's very, very simple. We'll see how simple it is. And it says this: suppose we've got some pasting context gamma. Then suppose in the lower boundary, we've got a term of some type. And suppose also in the upper boundary, there's some other term of the same type. Then in gamma, the whole pasting context, we get a composite term in the Hobbes set from U to V. So if you're not used to type theory, it seems like a funny notation, but you've got to accept it's pretty compact. So let's see an example. So this was our pasting context from before. This was its lower boundary delta minus gamma. Suppose we've got some term U living over here. So it could be F composed with J, could be F composed with J, composed with the identity on Z, or it could be maybe the identity on X composed with F, composed with the identity on Y, composed with J, anything that lives here. And suppose we've got something similar over the target boundary, delta plus gamma, which we call V. Then we can apply this rule, and we're just given, as if by magic, a new two-morphism, which is called the composite of this context gamma, of all these things, with respect to U and V. So what is this thing? It's a two-morphism. Which infinity category is it living in? It's living in the free infinity category on these generators, the free weak infinity category on these generators. And what Hom set is it in? Well, it's in Hom U comma V. U was this one morphism, composite of these guys, and V was this one morphism, composite of these guys. Very, very simple idea. Side condition here is that U and V must be full. So what that means is U and V have to use all of the variables. So we couldn't take U to just be F, for example, because that would leave out J. That wouldn't be allowed. Now, by the way, this goes back to Grothendieck. This is basically Grothendieck's original idea for what an infinity category is. I think it's exceptionally beautiful, and I think it connects to things in physics like holography and ADS-CFT. I have a training in physics, so I can't help thinking like that. I think we don't spend enough time in high category theory sort of meditating on the poetry of what we're doing. And I think it's very beautiful, simple idea, which is well known in a sort of complicated way, but I don't think people talk about it in a simple way often enough. So I think it's a simple idea. Okay, so this is how we build composites. But now, how do we build coherences? These are things like associators or unitors, things that are going to be invertible in our higher theory. How do we build these? Well, in almost exactly the same way. The rule is only changed a little bit. The only difference is that we don't have these deltas here. So what does this say? If in some pasting context, you've got some full term U of some type A, and in the same context, you've got another term V also of type A, then there's a law that says U equals V, basically. And we call this co-gamma U comma V, and it's in the Hom set U comma V. So let's see this in this sort of style. If in the context gamma, in this free infinity category on gamma, we can find some morphism U, which again is full, it has to use all the variables, context, mu, nu, and j. Suppose we've got some other k-morphism V, which has got the same type A as U did. Then we're given, as if by magic, for free, as it were, using this rule, we're given an invertible. So this will, if U and V were 2 cells, this will now be a 3 cell, because look, it's in the Hom category U comma V. So if U and V were 2 cells, it has to be a 3 cell. And we can interpret this as saying like U is equivalent to V. So it's like an associator or a unitor or something like that. All right. So I really would love it if someone would shout something out, just so I can tell I haven't died and gone to purgatory or something like that, which sometimes I feel when I'm stuck in a room by myself, but it's okay.
Yep.
All right.
So far, so good.
Yeah. Oh, thanks so much.
You're not alone.
Okay. You're not alone either. Great. Okay. Okay, so let's see some examples. See how easy this is. What's the first thing that we might want to do in a weak infinity category? We might want to compose some more morphisms. So let's work in the free infinity category on these generators. Objects x, y, z, morphisms f from x to y, g from y to z. This is a pasting context. It arises from one of these trees in the way that I described. So what do we have to give? This is the rule up here. We have to give the context, and then we have to give a morphism in the source and a morphism in the target. Well, the source of this context is just x. So in the free infinity category on x, there's only one object, that's x. And in the target is z, so we give z. So here we have, the syntax tells us that here is a new morphism, comp blah x comma z. And we interpret this as the binary composite of f and g. So we define the binary composite of f and g to be this thing. So why do we do that? Well, because it will turn out to have all the properties of the binary composite of f and g. Here's something else we can do in this approach. We can have unary composites. So this is like a bracketing of just a thing. It's like a unary composite of f with itself. So we do this like this, comp f from x to y, and we interpret this as a unary composite. What about an identity one cell? This is a coherence law, not a composite. We do it like this. In the free infinity category on an object x, we can find an object x, and we can also find an object x. So we satisfy this because we found something of some type and something else of the same type, namely just x is an object. So we've chosen u and v the same way. So we must get back a coherence law. In this case, x comma x comma x, and it's got type x to x, and we will interpret this as the identity one cell on x. So this, maybe this will be unfamiliar to you. So this is nice. This might be unfamiliar to you if you're used to the sort of traditional algebraic definitions of category and high category, which is finite and binary, where we say we have binary compositions and so on. This is unbiased. So just as we have binary composites, we also have unary composites, we also have ternary composites, and we have all sorts of composites. In fact, we have an infinite number of fundamental composition operations. So that seems horrific. Why would we want to do this? Compare it to the definition of a category where we just have, or a bicategory where we have a finite number of composition operations. The reason we do it is because it actually makes things simpler, right? If you look at the algebraic definition of tricategory, it's absolutely horrific. I mean, well done for people who've worked on that stuff. It's very impressive. And it, of course, useful for some purposes to have it written out in finite form. But in this unbiased form, we're already done. I mean, this is it. We've already finished giving the whole definition of infinity category already. We're just looking at examples now. And of course, we can obtain richer things like this. If P and Q are arbitrary one morphisms in some other infinity category, we can just apply a functor from a strict functor from the free infinity category on F and G. So we can compose F with G in this free infinity category to get this thing, which we had up here, comp blah. So that is like the primordial composed pair of one morphisms just living in this free infinity category, free on two one morphisms. Then we can just apply a functor to map that into any other infinity category. And that's how we compose one morphisms in any other free infinity category. And we use these square brackets. So this is saying F, this is our functor syntax. This means F is being sent to P, G is being sent to Q. I hope that's sort of meaningful. And here's another example. Because of course, when we choose U and V here, we can choose arbitrary terms, in particular, terms that have been constructed by previous uses of the comp rule or the co-rule. So these things can get syntactically complicated. So this is a coherence rule that says the identity composed with F is equivalent to F. So it arises by our coherence rule. So we can think of that as a uniter. And here's an example of an associator. In the free infinity category on three composable one morphisms, we're going to apply this co-rule. We can certainly find this morphism, F composed with G, composed with H, in this biased way. We can also find this one, F composed with G, composed with H, in this other biased way. And this, so we apply the co-law, and it says this bracketing is equivalent to this bracketing. So that's the thing we call the associator. So all the things that we expect to see in an algebraic theory of infinity categories, we can really find them here, really very easily. And because this is implemented on a computer, we can tell the computer what it is. The computer can check we haven't made a mistake, which is super useful. Okay, so far, though, this is all about free infinity categories. So that's nice, free weak infinity categories. What about actual infinity categories, which might not be?
Jamie,
Yeah,
can I interrupt for your
yeah.
non-loneliness pleasure? So on the previous thing, we could also get FGH together all as a list, right?
Absolutely. So then we could have had a ternary composite, but we just didn't do that example.
Right, okay, great.
Yeah. So definition, the category Catt P has got pasting context as objects and for substitutions. Substitutions, just this funny type 3 word for functor, strict functors as morphisms. It's a perfectly good one category. Now, we have some nice colimits in this one category. In particular, if we take the things that look like disks, so here's a 1 disk, here's a 2 disk, here's a 0 disk, and we take a certain family of pushouts, which I won't, of colimits, which I won't, they're very simple to describe. I won't describe them formally here. Basically just says we can glue together these disks to get this guy. That sort of makes sense, right? Because this guy is glued by taking this two cell, this 2 cell, this 1 cell, gluing them across their respective boundaries. We can really do that as a colimit in Catt P. So that's nice. And now we already have a definition of infinity category. It's a pre-sheaf on Catt P, which preserves these colimits. And that's it. That's the simplest definition of infinity category I've ever seen. Maybe the simplest you've ever seen as well. You'll have to tell me. So this is not my definition. This definition in this form goes to Eric Finster's Samuel Mimram in that Licks paper that I referenced earlier from a few years ago. This is known to agree via a huge chain of work done by other people. The original definition of contractible infinity category originally goes back to Grothendieck, and Meltzer-Niotis cleaned it up a bit. Batanin, they work really with infinity groupoids. Batanin said, hang on, you don't need to, this also works for infinity categories, not just infinity groupoids. Tom Leinster wrote a whole book about this. Bruno Reed did some nice stuff recently. And it's known that all these people's work is basically equivalent. Everyone's using a different notation, a different approach, but the work has been done to check it's all equivalent, and particularly this work recently by Arrowbook and Benjamin. And I think that the particular presentation by Eric Finster, Samuel Mimram, is really nice and really lightweight. In particular, so if you read Tom Leinster's book, it's wonderful. It's about operads mostly, but you don't. And he builds up at the end of his book to defining what these contractible infinity categories are. I mean, you have to get hundreds of pages through his beautiful book, and they're beautiful 200 pages. But if you just want to know what an infinity category is in a precise way, we've already done it. Right? You don't need this globular operand technology. So what Tom Leinster does and what Batanin effectively does is they set up this globular operand technology, and then they define weak infinity categories as in terms of certain sorts of globular operand. In this approach, we define the infinity categories elementarily, I guess, and then we could prove a theorem saying that they have a globular operand structure. But we don't have to do that. We could just get on and use the infinity categories. And we also, and Groth and Deacon Maltsignotis, they talk about globular extensions, which is the technology that's ultimately doing the same thing as these rules, but I find it easier to understand in this type theory way. Okay, so let's crack on. We need to get to the strict units. So in this language of free infinity categories, finitely generated infinity categories, we can talk about spheres and disks in a nice way. So spheres are going to be types, that is, they can be like HOM sets, and disks are going to be like context, that is, disks are going to be like free infinity categories. So let's see why that is. We start with a -1 sphere, which matching topological convention is like the point. So for us, this was like the type of objects. This is like the HOM set in which objects live, like a fake HOM set we've created, just so we have a HOM set to put the objects in so they don't feel left out. So now what's the 0 disk? Well, it's the free infinity category on these generated by a single generator, D0, whose type is the 0 sphere. So whose type is just an object. So that seems to make sense. The 0 disk should be like a point. And yes, we're saying in this language, it corresponds to the free infinity category on a single object. Seems to make sense. So now what's the recursive step? We say that the n sphere is the HOM set from an n disk to like another parallel copy of the same n disk. And we say that the n+1 disk, how do we get that? Well, we get an n disk. We get another copy of an n disk. And then we glue on a filler in between them. So this very simple idea, which maybe this be stated here very precisely, which might obfuscate a bit. So let's just see some examples. So this is capital D0. This context here just contains a generating object. This is capital D1, contains 2 points and a morphism. So capital D1 is the free infinity category on a 1 morphism. This is capital D2, the free infinity category on 2 0 cells, 2 1 cells, and a 2 cell. Right? So this looks like a point, looks like a 1 disk, looks like a 2 disk. So that's what our disks look like. Now, if we want to have a theory of strictly unital infinity categories, we obviously need to know what the units are. So what are the identities? It's very easy to define identities in this setup. We use this coherence law. For an n cell F, we define its identity as an n+1 cell as follows. Id F is defined to be a coherence over the n disk. So for example, over the 1 disk, let's take this example. For the source of the coherence, we take dn, d1 in this example. For the target, we also take dn, d1 in this example. So if we just go up to this point, right, up to this right bracket, then this is like the identity on d1 in this free infinity category. So the identity on the primordial 1 morphism. But then the way we get the identity on any other arbitrary 1 morphism is we just apply a functor, where we send D1 to whatever morphism F we care about. So we use this same trick as before. We build the primordial identity in this disk context, and then we map it out. That works very nicely. Okay, so now in just 2 slides, we're going to see how to make this theory strictly unital. What does it mean to be strictly unital? Okay, so the fanciest bit comes first, then it gets easier. So if you want to concentrate on 1 slide, this is the one to concentrate on. Okay, so suppose mu is a generator in our context gamma. So it's one of the generators of this free infinity context gamma, is locally maximal. So remember, that means that it's not the source or target of anything else. And suppose we have some functor sigma. Remember, mu is living in here. And suppose this functor sigma sends mu to an identity. This is our notation for mu under the image of the functor sigma. Then what we can do is the following. Well, we can say, okay, if sigma is going to take mu and send it to an identity in delta, then sigma as a functor must factorize via a first functor, which sends it to an infinity category freely generated on gamma / mu. This is almost exactly the same generating data as gamma. It's just we've thrown away mu. We don't need mu as a generator anymore. We've collapsed the context around mu. And then, and in particular, we have a functor from here to here, which sends mu to the identity on its boundary. And then we have a second functor that just does loads of other junk, just like whatever else sigma did, because sigma is some arbitrary functor with this property of sending mu to an identity. So we factorize it as a first bit, which sends mu, this first thing pi, sub mu, sends mu to an identity and everything else it leaves alone. And then we do sigma slash mu, which is everything else. And this commutes strictly. This is a commuting triangle of strict functors. So let's see an example, make that much clearer, I hope. So suppose this is gamma.
Jamie, is gamma mod u a context?
Gamma mod mu is a context, yes, because this is a commuting triangle of functors. Okay. So gamma is generating data for infinity category, i.e. a context. So is gamma slash mu. So is delta. Sigma is a strict functor between the free weak infinity category on mu to the free infinity weak category on delta, and likewise for these guys. All right. Okay, so let's see what happens in principle. Suppose sigma is this context, the one we've seen many times. And so, excuse me, suppose gamma is this context. And suppose sigma sends mu to an identity, delta. So what's gamma slash mu? It's the context where we take gamma and we take mu and we pinch it out. It's like we reach in with our fingers and we just pinch mu, we crush it, like killing a little insect. All the wasps have been coming out here. I've been killing them with my wasp racket. It's a very similar process, right? So we squash away mu. So now look, it's gone. Mu's gone here. This is gamma slash mu. So, but note, of course, it isn't that we've ripped out mu. If we rip mu out, we would still have f and g separately. It's not what we're doing. We're squashing mu. So we are having to, f is like collapsing into g or something like that, okay? So now what's this functor? Well, everything is sent to itself. J is sent to J, Z is sent to Z, Y is sent to Y, etc. G is sent to G. F, though, is sent to G because we've collapsed mu. And what is mu sent to? Mu is sent to the identity on G, right? Makes sense. And it's a perfectly valid functor. And if sigma had the property of sending mu to an identity, sigma must factorize through this functor. It's the beauty of this system. Right? This is supposed to be, this is the wow, this is like the only wow moment of the whole talk. So I hope you're feeling the wow, okay? So if we've got, just to say it again, if we've got a strict functor that could do any crazy stuff, but in particular it sends mu to an identity, sigma must factorize through pi mu, which is this really silly functor that all it does is send mu to an identity and nothing else. Okay. And the intuition, we call this pruning, because the intuition, so on the level of the Batanin tree, I'm not going to draw the Batanin tree again later, but if we go back to these nice Batanin trees, the intuition is that we've clipped off this whole branch. That's why we call it pruning. Okay, so how do we find the reduction formally in terms of this syntax? Well, if this was this was our setting, gamma, sigma, and so on, and if we had this composite over the context gamma with terms u and v, and we were applying some functor sigma, then after the pruning, instead of having a composite over gamma, you see, we've now got a composite over gamma slash mu. I'm assuming you can all see my cursor, by the way, because I've been doing lots of mad gesturing. That's great. We've now got a composite over gamma slash mu. So where originally we were composing over these three guys, now we're just composing over these guys. Mu has completely disappeared. And these terms, u and v, which are like the source and target of the composite, they lived in gamma. What we've done is we've applied the functor pi mu, you see, to take u and v that lived in here, and we've sent them down here. So we have simplified our expression, because this composite is now over gamma slash mu. It's a smaller context than gamma, right? It's a free infinity category on less stuff. So we've really simplified our composite. So it's like saying, if you were going to compose over this stuff, and you were going to compose some j, some nu, and some mu, but the thing you were going to compose at position mu was an identity, don't bother composing over here, just composing over here, because you can just use the identity on G if you want, and it plays the same role. Is that intuition clear? That's the idea. Except there's a funny side condition, side thing here. If the term we've got is already an identity, don't reduce it. The reason for that is that there are some corner cases where things can reduce into themselves and we get some infinite loops, and we just don't want that. So it's a technical thing that you can ignore. Okay, so that was the main thing. That was the main idea of the whole talk. So now a few things that are simpler. So this was prune identity arguments. If you were composing with an identity, don't bother. Just throw the identity away instead. That was P reduction. Now D reduction. This is throw away unary composites. So recall we have these disk contexts. With these disk context, we can build unary composites. For example, what's the unary composite of a one morphism? It's comp over D1 from D0 to D0 prime. And that's like the bracketing of F, the unary composite of F by itself. In a strictly unital world, we don't need to distinguish this from F itself. This is not helpful for us in any way. It's going to have the same type as F, lives in the same Hom set as F. We just don't want to see this. So we introduce a rule that says whenever you have a unary composite of some morphism U, of some n cell U, then just reduce that to U. Simplify that to U. Okay, and now for our final idea. The final idea is eliminating loops, which I think of like eliminating useless coherence laws. So consider a term as follows: co-gamma UU. So this is like a law, a bit like an associativity law or a unit law or something that says U is the same as U. Okay, so fine, we can build that, but it's a completely stupid coherence law, right? It's like saying F composed G is isomorphic to F composed G. Well, yes, that's true. It's sort of obvious because we could choose the identity. And indeed, there's a canonical coherence law of this type, just the identity on this thing. We didn't need this other fancy thing. So we simplify as follows. So whenever we have a coherence law that says U is equal to U, we say we throw that away. It's perfectly good composite morphism in the contractible infinity category, right? According to Grothendieck, this would be a perfectly good thing to build, but we're going to give a simplification rule, which whenever we see this, we throw it away and just replace it with the identity on U, because that's perfectly good. It just says the same thing. Different way to build something that says the same thing. Except again, we have one of these funny things. If the thing we've got is already an identity, we don't want to turn it into an identity because that would just never stop. It would be an infinite cycle, clearly. We'd be turning it into itself. We don't want that because we want simplification to terminate. So now we proved the main theorem of our paper is that if you have a composite morphism and you apply this simplification operation everywhere you can, so in all the arguments, so if you've got some functor, in every argument of the functor, everywhere you can see inside your composite, so you can do P reduction, D reduction, L reduction, wherever you want, then we prove that this simplification process will finish after finitely many steps, and the normal form that you get out is unique. So there could have been different choices. You could have chosen to do some L reduction first and then some D reduction, or maybe some P reduction first and then some D reduction. We prove that whatever you choose, you get the same simplified term at the end. In computer science, this is called confluence. And this means it's really easy for a computer to apply, because you can just tell the computer to apply these rules in any order greedily as quickly as it can find them. And then you're guaranteed it doesn't matter what you get out. Okay, so now let's see a bunch of examples of this in action. So at the top, we're just summarizing our rules. So P, our pruning relation, which says if you're composing with an identity, just throw the identity away and just compose with the other stuff. Don't bother composing with the identity. There's no point. The disk removal relation, which says unary composites. This is a typo. This should be an F here. It says unary composites can just be simplified by the thing itself. And this is this loop reduction removal rule that says if you've got a coherence law that says U is equal to U, just replace that with U. Okay, so let's try it out. Now, this is definitely going to involve some audience participation. So the first thing we're going to look at is F compose, so F is a one morphism, F composed with the identity on Y. So we're saying like F is a one morphism from X to Y, and we're composing it with the identity on Y. So in a strictly unital one category or infinity category or two categories, think of a strictly unital two category if you like, what would we hope this would simplify to? Are there any suggestions? Or hopes, dreams, or wishes? I mean, if it simplified to just F itself, I mean, I think we're pretty pleased with that, right? Because in a strictly unital infinity category, F composed with an identity should just be the same thing as F. It shouldn't be some other thing that's just isomorphic to F. It should literally be F. And that's the whole point about what our simplification law is supposed to do. So let's see what we do. So what do we mean formally by this? Remember, this was the thing that we said was the definition of binary composition. So we're doing binary composition, but then we're applying the functor where F is sent to F and G is sent to the identity on Y. So this is what we mean to compose F the identity on Y. We take the free infinity category on a pair of morphisms, we build the primordial composite of those morphisms, then we apply a functor, sending F to F, G to identity on Y. Great. So now what do we do? So the first step is we prune. You see, because G is being this functor is sending G to an identity, so we can prune it away, so it just disappears. Look, it's gone. It's been squashed like a wasp. And now what are we left with? It's a unary composite. It's the unary composite of F. So we use disk removal and we get to F. Fantastic. So the idea is that to work in a strictly unital setting, then if any two composites are related by this simplification strategy, we're going to treat them as identical. We're going to quotient by this notion of simplification. So in other words, that after this quotient, F composed with the identity on Y will literally be the same morphism as F. That's exactly what we want. That's what we mean by being strictly unital. Tick. Great. So now, next step, left uniter, lambda F. So this is a law. So we use this co-rule. We say in the free infinity category on a one morphism, if we have the identity on X composed with F, then that should be equivalent to just having F. So that's lambda F. So what should this simplify to? In a strictly unital infinity category, what would we hope it could simplify
The identity on F.
Great, great. That's the right answer. That makes a lot of sense. And indeed, for example, in a strict 2 category, I mean, they do have uniters and their identities. So let's check. So first we can prune. So why can we prune? Oh, because this guy in here is basically the same as the thing here. You see, this guy that's inside here is the same as the whole first example. You see, the first thing we did was prune to get this unary composite. So it's the same as before. And then we can do disk removal to turn this unary composite just into this guy. So now we have a coherence law that says in the free infinity category on F, F is the same as F. But that was our definition of the identity on F. So it's worked. So lambda F has just simplified to the identity on F. So in a world where we actually identify morphisms when they have this, when one simplifies to the other, then what this means is that in that quotient, lambda F is identified with the identity on F. Great, just what Omar wanted. Tick for Omar. Okay, so now it's a bit more interesting. An associator that involves an identity. So we're supposed to have got 3 composable one morphisms: F, the identity on Y, and G. So it's an associator. Now maybe there's someone here who already knows this from the theory okay, this could go different ways in different settings, but what's our hope here? So we're associating F, the identity on Y, and G, right? There's 2 ways we could compose these with binary composites: left bracketed or right bracketed. The associator says they're equivalent. What might we hope that this associator simplifies to in the strictly unital world? So let's see. Let's see. Maybe if anyone feels bold, they could shout it out and I'll get some brownie points. So this is the definition of the associator. So let's just remind ourselves, in the free infinity category on 3 one morphisms, there's certainly a law that says F composed with G composed with H is equivalent to F composed with G composed with H. But now we apply a functor. So this is the associator. This is the associator as a morphism in the free infinity category on these generators. But now we apply a functor that goes into our target category, whatever category, infinity category we're actually working in, where we choose to send F to F, G to the identity on Y, and we send H to G. Is that clear? These 3 guys are in the same order as these 3 guys. Okay. So the first thing we do is a pruning, because look, G is a locally maximal guy. It's not the boundary of any other generator, and it's being substituted for an identity. So we throw it away. We rip it out like a wasp. We kill it. And now it's gone, you see. We've just got F and H left. Okay, H has been renamed G. Maybe that would have been clearer if I hadn't done that renaming. And this G has just turned into the identity on Y. Okay, so that's what we've got now. So what can we do now? We can do, now we do some more prunings, because look, we've got F composed with an identity on Y. That was exactly the same as this thing. So you see the pruning was the first thing that we did. So we prune here and we prune here to get the unary composite. So this goes to the unary composite on F. This goes to the unary composite on G. And now we can remove these unary composites, disk removal. And now we have a coherence law that says in the free infinity category on two composable one morphisms, F composed with G is isomorphic to F composed with G. But that's obvious. There's a canonical representation of that. It's just the identity on F composed with G. And that was what our loop simplification rule did. So I like this example because we use all three different types of reduction: pruning reduction, disk reductions, and loop reductions. And what we're told the answer is the identity on F composed with G. And I think that's sort of a nice answer. In a strictly unital infinity category, what should this associator be? Well, it's something that goes from F composed with id Y, the source of this associator should be F composed with id Y, all composed with G. Well, in a strictly unital infinity category, F composed with id Y should just be F. So the source of this associator is just going to be F composed with Y, F composed with G, and the target of the associator is just going to be F composed with G. So a really nice thing for this associator to be in a strictly unital infinity category is just the identity on F composed with G. And that's what we see. Okay, so now we can define a strictly unital infinity category in a very easy way. So we define a one category cat P SU. We start with cat P. Remember, that had objects given by pasting context, these Bertanin trees, and one morphisms given by these strict functors. But then we apply this quotient. So if any two composite morphisms have got the same normal form, we identify them. We take the quotient. So there's obviously a functor from cat P to cat P SU, because cat P SU is a quotient of cat P, and it's obviously full, right? Okay, great. Now remember the definition of infinity category. It's a contravariant functor, pre-chiffon cat P, that preserves globular sums. So now we have a super easy definition. A strictly unital infinity category is just an ordinary infinity category that has the property of factoring through pi. Now that's great, because for an infinity category, being strictly unital should be a property, shouldn't be like extra structure. Should be something that we just check. And that's exactly what's borne out here. So what does that checking amount to? Well, it amounts to checking that if you've got a particular infinity category, one of these pre-sheaves, then you need to check that if I've got any two operations that within the same equivalence class, for example, lambda F and the identity on F, we have to check that they act in the same way. We have to check that this for all of these things. So it's a lot to check, but if it's the case, then we'll factorize. So there's been one previous paper on strictly unital infinity categories by Bertanin, Chisinski, and Weber. Our definition seems to be strictly stronger than theirs. Their work inspired us a lot. We build on what they do. Their work doesn't let you. Their work is a bit less explicit than our work. So in their work, they can't start with something and then see what it reduces to. It's not as concrete as that. So maybe you could say, like, in principle, you could decide if these things are equivalent, but in practice, you might not know how to do that, right? It's not a constructive thing. Ours is more constructive. And it also seems that it's stronger, because it doesn't seem like they have any analog of this loop removal rule. So I believe in the Bertanin, Chisinski, Weber definition of strictly into infinity categories, they would not have that this associator would be the same as this identity, for example. Okay. And now conjecture, work in progress. Every infinity category is weakly equivalent to a strictly unital infinity category. That's something we're pretty close to, but we can't announce that yet. Okay, so now just to close in the last few minutes, some applications. So let's do a little bit of homotopy theory with these ideas. So suppose we are working in the free infinity category on these generators. So let's see what this means. We've got an object X. We've got a two-morphism S, whose source is the identity on X and whose target is the identity on X. And we've got another two-morphism T with the same type as S and the same HOM set as S. Its source is the identity on X and its target is the identity on X. So we're going to work with a free weak infinity category on this signature. Great. Now, the Ekman-Hilton argument is a really beautiful observation, which I'm sure is well known to everybody here, maybe not in this language, that if we take S and T as two morphisms and we compose them as two morphisms, we compose them vertically as two morphisms, then S composed with T is isomorphic to T composed with S. This is very well known in homotopy theory and in category theory. This is like the first interesting phenomenon, surprising phenomenon of high category theory. Now, in Catt's strictly unital, we can construct it very easily as an interchanger like this. We call this interchanger U. We construct it using our co-law. And the co-law says that this guy, this funny composite, so here we get T, we horizontally compose it with an identity 2 cell. Here we get S, and we horizontally compose on the other side with an identity 2 cell. And then we vertically compose those guys. It's isomorphic to this other thing. We build this interchanger. It takes about as much time as it does to type this out in the computer as it does to make this LaTeX picture. And then it's it. We're finished. This is the Ekman-Hilton argument. But why, you might ask? Because the Ekman-Hilton cell is supposed to have the source S1 composed with T, but this is much more complicated. It doesn't look like S1 composed with T. Well, let's see why. So let's look on this side. So remember, when we work in the strictly unital world, then if one term simplifies to another term, we identify them. They are the same one morphism. The morphisms in strictly unital world are equivalence classes of composites, not composites on the nose. So the point is that this guy is not this guy on the nose, but it's in the same equivalence class. So let's see why. So first we do some pruning. So we see here, this T is being composed with an identity. So we can throw that identity away, and you see it's gone. We've just got T. Here we've got S, and we're composing it with an identity. We throw that identity away, and we have S. Thanks for nodding. Omar Juan, you're nodding. It's giving me so many positive endorphins. Very kind of you. Okay. And now we see, what do we have here? It's kind of hard to tell because I'm using a funny syntax to fit it on one page. But this thing is really now the unary composite of S. Sorry. So let's just replace it with S. And this is just like the unary composite of T. So replace it with T. So now look, we have got the vertical composite of S with T, and it's the same on the other side. So we build this guy. But now, according to the type theory, or rather in the theory of strictly unital infinity categories, this guy is identical to the vertical composite of S and T, and this guy is identical to the vertical composite of T and S. So now, okay, so that's nice. We can do this in the strictly unital theory of weak infinity categories. But we can also prove this in the non-strictly unital theory. That means in the fully weak theory where units aren't strict. And when we do this, it's much, much more complicated. We can build the proof. It's a complex syntactic object. We build its syntax tree. So that's the tree where objects are morphisms, and then there's like an arrow to all the. So the morphism we're building is a composite of other morphisms, and those composites are composites of other things. So we get a big tree, and this is the tree we get in Catt. So the fully weak theory, and we can count this syntax tree. It's got over 1,000 vertices. Now, the proof in the fully weak theory is much, much more complicated than what we just did here. Let's see why. Let's look at this first simplification step, where here we threw away this identity guy. We just got this. And we might say, okay, so how are we going to adapt this proof in the fully weak theory where we don't have strict units? We might say, well, this guy, T, horizontally composed with an identity, it's not identical to T, but maybe it's isomorphic to T or something. But it's not. Because this guy, T horizontally composed with an identity, is not even parallel to T, right? Because look at what's the type of T horizontally composed with an identity? It's a two morphism. Its source is id compose id. Its target is id compose id. So it's in the HOM set, id compose id, comma, id compose id. That's a different HOM set to this guy. It's just in the HOM set id, comma, id. So this guy, the horizontal composite of T with an identity, is not even parallel to T. So in order to actually, you can do this in the fully weak theory, but it's vastly more complicated. You have to insert loads of units like lambdas and rows. They have to bubble around. It's really horrific. And that's why you get this huge syntax tree. Now this guy, but in the strictly unital theory, this is the whole proof. This is already the whole proof. And this is the syntax tree in Catt-SU. Okay. Now the syntax tree, this is like what you actually have to write out as a mathematician to give the fully rigorous composite. So obviously this is much simpler, 20 times smaller, and I've drawn it to the same scale for sort of comedy value. This is the drawn to nicer scale. So what this is telling us is that if we use the strictly unital theory rather than the fully weak theory to write down formally the simplest non-trivial homotopical phenomenon of high category theory, we get a 20-fold improvement in complexity. Conjecturally with no loss at all, right? Because we conjecture that every weak infinity category is equivalent to a strictly unital one. So in particular, if we prove this and we're very close, blah, 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 but we haven't quite done it yet, then we would have an algorithm that takes this and reinflates it back up to this. That's the idea. We don't have that yet. But certainly we feel confident in saying that, you know, if all you want to do is investigate building homotopies in a way that's easy for you as a mathematician, and you want to remember our motivation right at the beginning of the talk, you don't have to bother with all these lambdas and rows and stuff everywhere, then you can work in this strictly unital theory and the computer will take care of that for you. So now I'm almost finished. I'm running over a few minutes. Sorry about that, but this is pretty cool. So this is the solipsis. The solipsis is a 5-cell. It's in this slightly more complicated context. X is an object. S is a 3-cell from the identity on X to the identity on the identity on X, right? So everything's got one like level more complicated. So here S went from an identity to an identity. Here S goes from a double identity to a double identity. What we find here is if we do the Ekman-Hilton braid, so we braid S around T, and then we braid S around T again. So this is a mistake. This inverse shouldn't be there. This isn't a braid and an inverse braid. It's a braid and another braid. So these guys should not cancel out. But they do. The double braid is equivalent to the identity. This is the source of symmetry in symmetric model categories, right? A symmetric model category is a 4-category with 1 0-cell, 1 1-cell, and 1 2-cell. For this reason, because the braiding collapses. And we can formalize this in Catt-SU. Its syntax tree has got about 2,000 vertices. And at the time that we formalized this, we believe this was the first ever formalization of the solipsis in type theory. Since doing this, a bunch of homotopy type theorists have come out of the woodwork and formalized it in homotopy type theory, but we did this first. It's great that they've done it as well. But the point is our language was the strictly unital language made this easy to do. So we can't formalize the solipsis in Catt. So the fully weak theory, it's just too hard for us to do. Of course, if we had this conjecture, then we could do it, or we could run an algorithm on this solipsis formalization, and we would get back the full solipsis formalization in the more rigorous fully weak, not more rigorous, but in the fully weak theory. And it would be nice to see how big that is. I mean, it's an easy estimate. If we just say here, look, the fully weak Ekman-Hilton argument was 20 times bigger than the strictly unital Ekman-Hilton argument. I mean, it could easily have like 100,000 vertices, right? So we are getting epic improved simplifications here, right? Okay, so this is the end of my talk. So higher categories are not contractible things, okay? We have path relevance and so on. We have weak structure. So if we have F that goes from X to Y and Y goes from Y prime, excuse me, F goes from X to Y and G goes from Y prime to Z, some like infinity groupoid, we can't necessarily compose F and G because Y might not be the same as Y prime. But the point is we can sort of carve our infinity groupoid into contractible pieces. So maybe Y and Y prime are the same modulo the unit structure. in which case now we have a way to compose them, and that can be useful. So what about extensions to this work? Well, an obvious extension is what about associators? So gray categories are 3 categories with strict units and strict associators. And we think that we can apply the same sorts of ideas to strict associators as well. That's work that I'm doing in particular with the student Alex Rice and Eric Finster, who's my postdoc. I think Alex might be here at the moment. So we're looking at that. We think it all works for the strict associators as well. Could these ideas of semi-strictness apply beyond composition? So this is all in this type theory, which is very well, but all it lets us do is build composite morphisms in the free infinity category on some stuff. This is merely an infinity category. It doesn't have products or dependent sums or anything like that. Couldn't we have some of these advantages beyond merely compositional structure, maybe even in logical structure, right? Can we have a notion of semi-strict dependent sums or something like that that can make them much easier to work with in practice, remove the bureaucracy of proof construction in higher category theory? And how do these ideas relate to other approaches to semi-strict higher category theory? So I have this other completely different project, which is this proof assistant, homotopy.io, where you can point and click with your mouse to build geometrical composites like you're in some graphical design program. You could build arbitrary composite morphisms in high dimensions. And that setting is actually strictly unital and strictly associative. But it's a completely different project. The two don't relate to each other whatsoever, which is sort of crazy, right? And what we'd love to do is we'd love to, for these ideas of semi-strictness that we're working on, relate them to things like homotopy type theory. So for example, let's say someone is in homotopy. So homotopy type theory is a much more stronger logic because we have logical structure, right? What we're doing here is purely compositional. But say in homotopy type theory, they have what's called these encode-decode proofs, which are these nice ways to prove that some homotopy group has got certain structure. And that involves in particular constructing in homotopy type theory the generators for some homotopy group, and then showing that some relations are satisfied. Those sort of things they have to show are satisfied are very similar sorts of homotopical arguments to this Solipsis argument, this Ekman-Hilton argument. So I'm imagining a world where some clever homotopy type theorist is trying to build some encode-decode proof for like the 5th homotopy group of the 7th sphere, but there's some explicit homotopy that is hard to construct. So maybe we could construct it in this semi-strict world and then transport it back into the fully weak world, and then it could be inserted into that homotopy type theory proof, which again is very different, right? They use the J rule. They use this very different way of setting up their composites. So what we want to do is use these new techniques and get them to talk to these other techniques that other people are using. I think that could be really powerful and really fun. Okay, that's the end of my talk. Thanks a lot. Sorry for running over time a bit.
Thank you so much for the great talk.
Thank you very much.
Yeah, it was lovely. The talk was lovely, and it was great having you here. Well, are there any questions or comments for Jamie?
I don't know if there's anything you can say about this, but I was reminded: is there a conjecture of Carlos Simpson that goes almost in the opposite direction, that you can realize like weak n categories with everything strict except the units?
That's right.
Yeah.
So we tried to do
that always sounded crazy to me. This sounds more reasonable. I'm
right. I know what you mean. It does sound less plausible. So that's now been proved in a sense. There are some issues with the proof, but there's some nice work recently for infinity groupoids. It doesn't go as far, it's not like the full proof I would hope for, but it's certainly progress. So there's some sort of proof of Simpson's conjecture that every infinity groupoid is equivalent to an infinity groupoid with strict, with strict associators and strict interchangers. So we're the only weak structures in the weak unit. You're right, that is completely opposite to this. So I find that, and we have tried. So this other guy who's done that proof doesn't use our techniques, you use some different techniques. We've tried to do that using our techniques. It seems a lot harder for reasons that are, well, we don't understand. If we understood, then we could probably fix them. We could write a paper about it. But what I find amazing about that, you're right. So it's completely different. So what that means is, if we look at my little honeycomb, which was supposed to be a way to show how we can chop up an infinity groupoid into contractible pieces, what that means is there's another completely different way, like a dual way to chop it up. So imagine like we drew like the dual honeycomb on top. So what's weird about that is I could maybe take something like this F, I could find its strictly unital normal form, but then maybe I could transport that into its Simpson normal form, and it's going to move around. And then maybe I can transport it back into its strictly unital. Well, am I going to go back to where I started? Maybe I don't. Maybe I sort of march around. All sorts of crazy stuff
Right.
could happen. That's very rich and exciting. But to do that, we would have to get that Simpson stuff into this framework, and we've had some technical challenges doing that.
Thank you. Yeah.
Yeah, so by the way, I'd love to know more about you guys and what sort of stuff you do in your group. Maybe you could just introduce me a bit to who's here and what you guys work on, because I'd be really interested to find out about that.
I think most of the main members of the group are, well, the organizers are Omar and Carlos. And yeah, some of the regulars are Bob Paré, who left, sadly. I think he was busy, and David as well. So he left. So yeah, maybe, yeah, Carlos, do you want to say something?
Yeah, that'd be great.
Well, right now we are working in PetriNet. Yeah, we are really interested in how to presentate a monoidal category via PetriNet and also the stochastic stuff. Yeah, but just we are learning. Yeah,
I find that super interesting. For a long time, I thought about what would it mean to have some like higher version of PetriNets. So like. So PetriNets you can model with monoidal categories, right? So what if you had like what if you used like I don't know, monoidal bicategories or something? You had some high dimensional things. Could you use this to simulate stochastically some richer sorts of process?
Yeah, that's really interesting. Well, yeah, what would that look like? I mean, in a